everyone. I'm here to welcome you to this new old episode of Science Factory. Why do I say this? As I mentioned last week, I'm going to be posting old interviews that were originally released on La Fábrica de las Ciencias profile. And the one I have chosen is special because it's the only interview I have made to a scientist, not an Egyptologist. This is out of my comfort zone. Although I'm an engineer, this kind of science is not my field of expertise at all. So it was interesting, and I was eventually very happy that I could come up with more questions than the ones I had planned beforehand. And I hope you like it. I'm going to stop talking now, and I'm just going to leave you with Scot Rafkin. Good afternoon, everyone. As Jorge has already introduced, we have here today with us Scot Rafkin. Thank you, Scot, for being here with us. It's a great pleasure, as usual. For me, I have to say that, as I told you before, Scot, this is a different topic. I've been interviewing Egyptologists recently, but you're the first that is not an Egyptologist. So bear in mind that I'm not an expert in your topic, and please be patient with me. But we are very interested in getting to know you better. And so here's the questions. Please, could you tell us more about Mars Science Laboratory meteorological, I'm going to have a hard time with this, data analysis? Sorry for making mistakes with all these super long names.
That's okay, Alicia. It is a mouthful. It's a lot of words, meteorological. I'm happy to talk about the Mars Science Laboratory and the meteorology. I think maybe if it's okay, I'll just back up a little bit and just a big picture of what the Mars Science Laboratory is, which I think most people have probably heard of it at some point. It's also known as the Curiosity rover. Sometimes you'll hear it called by its name. But the Curiosity rover is the Mars Science Laboratory mission, which is led by NASA. There are lots of partners with NASA, including those in Spain. And the Spanish led the meteorology experiment that is on the rover. Okay, and that experiment is collecting data about Mars's atmosphere, temperature, pressure. It was collecting winds. That wind sensor has since stopped working. Remember that this rover has now been on the surface for more than 10 years. So it's lived much longer than we ever imagined. The wind sensor is no longer working. There's also some information about the solar radiation coming down, as well as ground temperature and some other things that are kind of related to the weather and climate of Mars. And that's the purpose of the data that we're collecting, weather data, the meteorological data that we're collecting from the rover. So we measure these things and we look at how does the temperature vary with time over the course of a day, over the course of months, over the course of years. And Mars has an amazingly interesting weather and climate system. In some ways, it's similar to Earth, but it's also very, very different. So we take all this data, we look at the temperature, we look at the pressure, we look at the winds, and we try to understand what are the weather systems on Mars, what is controlling the variations that we see, how does dust in the atmosphere affect the weather on Mars. It turns out on Mars, most people know Mars is a pretty dusty place. It's famous for its dust storms. Those have a huge impact on the weather and climate of Mars, so we try to understand that a little bit. And all of this also allows us to test whether our theories, hypotheses, and knowledge of how weather and climate works on Earth, whether that also works on Mars or not, right? So it's a kind of a wonderful natural laboratory to test these big ideas out.
And what are the most surprising findings, or what are the most important findings you have made so far?
Yeah. So there's lots of things that we knew about Mars from previous missions, because we have been to Mars prior to the Mars Science Laboratory. So some of the things I'll just point out, which I think are amazing, are, for example, the enormous day to night variation in temperature. So Mars is a cold place to start with. During the daytime, the temperatures might get a little bit above freezing, a little bit above 0 degrees Celsius, but most of the time, well below 0, like 100 degrees below, right? So huge variation. It gets very, very cold at night, starts to warm up a little bit during the day, but those variations are amazing. What's interesting about the particular place where Curiosity landed, which is in a large ancient impact crater called Gale Crater, is the crater itself. It's a big hole in the ground on Mars, and it drives incredibly interesting local weather. And so, like on Earth, we know if you're in the mountains or in valleys or other places, that topography often has a very strong influence on the weather, right? On Mars, it's even greater. And so,
is it like a microclimate?
Yes, exactly. Yes, exactly. A microclimate.
It's like in my hometown.
Yeah, right. And it's even, like, if you live even near the beach where there's no topography, the nearby ocean or the sea will influence your weather very strongly. On Mars, the topography has even greater control than it does on Earth. And so during the day, as the slopes of the crater heat up, it drives very, very strong winds upslope, away from the center of the crater and up the slopes. And at night, the flows reverse and flow very strongly down the crater. Right? And this happens on Earth, but on Mars, it's magnified. So it's a very, very strong cycle. The other interesting thing that happens is it's almost like the crater is breathing. Like during the day, it's exhaling and the air is coming out, right? And at night, the air pours back into the bottom of the crater. So it's kind of breathing like this. And what happens is if you look at the pressure associated with that, the pressure at the surface of the atmosphere changes tremendously by more than 10%. So it drops during the day when the air is going out of the crater, and then the pressure goes up when the air comes back into the crater. And just to give you some context, 10%, it's a huge number. That's about the difference between the typical surface Earth pressure and the center of a hurricane. That difference is about 10%, right? So every day the pressure in Gale Crater where the rover is, it's like as if the pressure is changing, as if a hurricane is coming to and from, back and forth and over you, right? So the pressure is going up and down tremendously, and this drives these wind systems as well. So it's a very dynamic place, very dynamic, very interesting. And that was a bit surprising to see that kind of strong pressure change. We expected that to be the case. We had done some theoretical models and some other things. But when we actually went there and measured it, we were able to confirm that and see it's a really remarkable thing.
It's interesting. So there were some ideas you already had in advance. Some of them were verified and some other new findings were done also or performed. Okay. Well, that's how science is in fact, right?
Right. Yes. And so one of the primary tools that we use, and one of the things that I work with, is weather modeling, to use our computer models, just like we do on Earth, to predict the weather, to understand the climate. And so, I have taken these Earth models that we use and I've modified them to work for Mars. And this has allowed me and others who do this to, even before the rover got there, to make predictions about the weather that we think we might see. And this is also part of science, is you have models, you have hypotheses, you have ideas, they make predictions, and then eventually you go and take the actual measurements and see whether you were right or wrong. And so, we did this in advance of the rover, and overall I think we did a pretty good job, but there are lots of, let's say, small details and other things that have surprised us or are allowing us to adjust our models a little bit to try and better represent what reality does.
Do you have any kind of competition amongst you and your colleagues to see if you're right and wrong?
Yeah, there is a competition. I would say it's a friendly competition.
Yeah, of
One thing
course.
that is really wonderful about I would say the field of planetary science, and even as you focus more down to the field of Mars science and Mars weather and climate sciences, it's a pretty small community. We all know each other pretty well, and so it's a wonderful environment to work. And of course, we have a friendly competition of trying to get new results and come up with new ideas or show that somebody's idea is wrong. I mean, as scientists, we spend a lot of time trying to show that our friends and our colleagues are wrong, right? And
Each other.
yeah, but it's a friendly competition, and so it definitely is, and but it's an important part because it's a motivation, and it drives the science forward.
And a challenge
Yeah,
also. And
yeah,
it's always very important to share ideas with your colleagues and different points
yeah.
of view. And I work also in a technical field in engineering. And for me, it's very important because when you're focused very deeply in a very specific task, you lose kind of sight of it. So it's very
Mhm.
important to give a step back, get some wider perspective, broader perspective, and also the ideas from colleagues are very important to implement in your
Yeah,
theories, in your research. So I guess you do that too. It
absolutely.
must be
Yeah,
very interesting.
yeah, absolutely. And I think the point that you just mentioned there, which is, none of us work by ourselves. Almost everything that we come up with is a collaboration, international collaboration. Again, it's such a small community, and it takes a lot of effort to get a spacecraft to Mars or to anywhere, right? So by its very nature, most of these programs are highly, highly international, right? So we all work together as one big community, and it's an amazing thing to see. It's an amazing thing to be part of, and it's fun and exciting, and it's motivating, and it really makes the job a wonderful experience.
Yeah, I can imagine it must be amazing. My next question is going to make me pronounce this super long name again. Now I wanted to talk about the characterization of Titan's planetary boundary layer through large eddy simulation. I hope I said it right.
You did, yes. So I'm going to start again, kind of backing up a little bit, talking about things in general.
Thanks.
Let's talk about Titan. Titan is a very large moon of Saturn. It's in fact the largest moon of Saturn, and it's roughly speaking even the size of our moon here on Earth. So it's a very big planetary body. It's also unique. Of all the moons in the solar system, and there are, I don't even know how many, hundreds, like Jupiter and Saturn have a whole bunch, but of all the moons, it is unique in that it has a thick atmosphere. Right? And and the atmosphere is actually thicker, more dense than Earth's atmosphere. And it's made primarily of nitrogen, just like Earth's atmosphere. Our atmosphere is mostly nitrogen. Um, but it also has a couple of trace gases, the most important being methane. We know methane on Earth is sometimes it's called natural gas, similar, okay? But Titan is also extremely cold. It's so cold that the water that you might find on Titan is frozen rock hard solid. It's as hard as a rock on Earth, okay? So that's the water on Titan. But the methane on Titan behaves just like water on Earth. It can be a liquid, it can be a gas in the atmosphere, or it can be a solid as an ice. And so it's possible on Titan to make methane clouds, just like we have water clouds on Earth. It's possible for it to rain on Titan, but it rains as methane. It's possible for it to snow even a little bit on Titan, but that snow is made of methane. And just like on Earth, when it rains, that water hits the surface and it has to go somewhere, and it can form lakes. So there are methane lakes on Titan. It's an amazing place. There's no other moon in the solar system like this. In fact, there's no other place no other planet other than Earth in the solar system that does this. So Earth and Titan are twins. They're the only two places in our solar system that have a thick atmosphere that with a surface that has lakes, and where it rains and there's clouds, and it kind of behaves just like the water cycle on Earth, the methane cycle on Titan. They're twins. And so we want to go there. We want to go to Titan, and with spacecraft, of course, and we want to measure it and study it some more. And we're doing that with a mission called Dragonfly. And Dragonfly is a drone. It's a rotorcraft. It will launch in July of 2028. It will take 6 years to get to the Saturn system. And when it gets there, it will enter directly into the atmosphere of Titan inside of a little protective spacecraft, what we call a heat shield. And as it slows in the atmosphere and a parachute comes out and it slowly starts to drift down towards the surface, that shell will open up and the Dragonfly rotorcraft will drop out. And its blades will fire up and it will start flying. And it will come down and start scouting for a safe place to land. And it will check it out. This is all autonomous. This is all robotic, okay, all by itself. And it'll eventually, hopefully, land safely on the surface, and we'll begin doing some experiments with that mission. It contains lots of instruments to study Titan. Okay. As you can imagine, we got to fly through the atmosphere, and we want to understand the atmosphere. So my interest comes in, number one, we need to understand the character of that atmosphere because we have to descend safely and land. We don't have a lot of data from Titan. We have only studied it very little with a few spacecraft. So we have very little data. So again, this is where my modeling comes in. We're trying to model the atmosphere of Titan because we don't have a lot of data. So the model will hopefully represent reality a little bit, and then we can help design the performance of Dragonfly so that it can operate safely in the atmosphere of Titan. Okay, now I'm going to answer your question. It's been a long way to get here, but hopefully that's okay.
Yeah, sure. Go ahead.
Okay. In the lower part of Titan's atmosphere, and actually in the lower part of Earth's atmosphere, there's a layer of the atmosphere that we call the planetary boundary layer, the PBL, planetary boundary layer. And it's the layer of the atmosphere that is most directly affected by and interacts with the surface, with the solid surface. And this layer is where Dragonfly is going to operate. It's sitting on the surface in the atmosphere, right? It's going to fly through the atmosphere and take measurements. All of this is happening in the planetary boundary layer. Just like on Earth, when the sun is up during the day, the ground heats up a little bit, and that produces turbulence. It produces thermals, relatively warm air that rises, and the colder air above sinks down a little bit, and you get turbulence in the atmosphere. This is how, eagles and hawks fly around on these thermals. If you have been in an airplane, you will know that it's often more turbulent to land and take off during the day as you come down into the boundary layer, right? So Titan is going to have to operate in this environment too, and we're modeling those things. We're modeling that turbulence. The turbulence is composed of eddies, of little circulations that swirl around. And so I'm using a model that actually tries to resolve the structure of those eddies and how they evolve through the day to try and understand how big they are, how strong they are, what's the scale of the upward motion in the eddies, what's the scale of the downward motion of the eddies, how much back and forth, left and right is there, how much turbulence is there, what can we expect the Dragonfly spacecraft to encounter as it descends and then ultimately flies off again to some other place. So that's the goal of characterizing the environment. The nice thing is Dragonfly will carry, just like the Mars Science Laboratory, Dragonfly carries some meteorological instruments. And so we'll be able to test the predictions. What is the temperature? What are the winds? What is the pressure? How much methane is there? So once we're there, we can test these predictions. But in order to get there safely, we have to make these predictions and hope that they're close enough that we will have a safe landing. Okay.
Questions regarding all this that you have been talking about. First question is about regarding the timing, because we are talking about a very long-term task project. Why? Because it's only arriving to Titan is going to take 6 years. So you are designing the drone and everything, like the material instrument that you will need to do that super long journey.
Yes.
And how is that regarding the project management? I mean, it's really difficult for me to visualize how you work in those terms. That's the first question. I don't know if I was clear, because the question is not absolutely clear in my head.
Very clear. Yes, I think so.
And the second question, because otherwise I'm going to forget. When you said that you were modeling the atmosphere,
yes.
What exactly do you mean? How do you model that?
Great. Okay. Yeah, so there's two questions, sort of one about the long-term nature of the project and the project management, and the second one about the sort of more details on the modeling. So, okay, let me answer the first one. I'll just say that, sending any mission on these planetary missions is one of the most remarkable things that humans do. It's one of the most complex things that humans do. And the journey itself, once it launches, will take 6 years. But the planning that goes into even getting to the launch is a decade or more in the making. Right? So if you rewind the clock, how did we even get here? Many, many, many years ago, somebody or some group of people said, hey, we should go to Titan. How can we do this? What should we do? Right? How are we going to do this? And they toss out ideas, and eventually you think about maybe a drone is the way to do that. And then you take that idea and you have to study it and come up with sort of the details of how do you even do that from an engineering standpoint. Then you have to propose this to NASA or the European Space Agency or other international agencies, usually a lot of them, get them all to agree, yeah, that's maybe not a bad idea, but it still has to be reviewed and competed against many other ideas, because other scientists want to go to other places, right? And there's not enough money and resources to do all these things. You can only do one at a time, more or less. So then you have to beat out all of those other competing ideas. And then the real project starts. And then you start working on more of the details of the engineering designs and these other things. And so we're still, like I said, it's not going to launch until 2028. So there's been a lot of work and design just to get to this point. And only in the last 6 months to a year has the spacecraft itself even started to become manufactured and assembled. And it's going to take all this time to do all that and put it all together, do an incredible amount of testing for exactly the reason that you're saying. It's a long trip. And the spacecraft and its instruments and all these things have to survive that long trip through deep space, which is cold, which is in a vacuum, which is potentially bombarded by all sorts of ionizing radiation that can damage electronics, can damage optics, can damage all kinds of things, right? And then when it gets there, it all has to work. And you only get one shot. Everything has to work perfectly.
For me, I'm sorry to interrupt, but as you're talking, I'm just picturing it. And as I told you, I work in engineering and I do other kind of projects. But I imagine what kind of, I mean, it's interesting in the big picture, but the practical side of the project, what kind of nightmare can it become? Because I'm thinking about like how my job is, that
Yes.
we struggle to agree about something, about the vendor of an equipment, about I don't know, the revision of the drawings, that they are not up to date. I mean, all these kind of things.
Yes.
And we do much shorter projects.
Yeah.
These are not complex projects. I do industrial plants. So it's a different scale, let's say,
Yeah.
but in a shorter period of time, and it's still a nightmare. So in such a long period of time, when also technologies are advancing. So how can you come up with the idea today
Yeah.
that
Yeah. So,
with the tools you have today to do something in 20 years time?
right, right. So lots of good questions there. From the project management side, it's incredible that any of these things ever make it to launch. There are, hundreds of people involved in getting this thing to the launch pad, and hundreds more once it launches. And they all have to work together somehow. It all has to be choreographed. Fortunately, we have past experience to rely on. This is not the first spacecraft. So over time, NASA and other agencies have built up a process by which you get from a drawing on a napkin, an idea, to something that's real, right? But and there are specific roles of people. So the missions are led by what we call a principal investigator. And it's a single person, and this is important, a single person who is effectively at some point the ultimate decision maker, right? They have a team, though. They have a very capable team that advises them and informs them. We have working side with them a project manager. This is someone who tracks the schedule, making sure everything is being done on time. They track the cost, making sure that things are being done on time and within budget, right? All these things. And they're supported by a system engineering team that is looking at the system as a whole to making sure all of the individual components are coming together properly. And those engineering teams have more engineering teams underneath them and more underneath them. And each one of those has a manager as well, right? And so it's this very hierarchical structure, right? And in the end, though, at the bottom are all the individual engineers, and it might just be one engineer who's working on a single mechanism for a door that springs open.
Yeah.
Right, but that feeds into some other subsystem, which feeds into something else, and it all comes together. And every single one of those tasks is tracked, and every single one of those tasks is documented, and there's a tremendous paper trail for everything. Right. So it's not just a science and engineering task, but it's an amazing management task of keeping everything together. And it's quite remarkable that it works, but it does somehow.
It's interdisciplinary because a lot of different disciplines are involved, all working together, and you end up creating a wonderful thing. So as you said, it's completely remarkable.
It is. Like I said, it's one of the most remarkable things that humans do. It's one of the most complex things that we do, right? And about new technology, this is one of the frustrating things. As I said, you start planning these and designing these 10 or more years past. At some point, your design is your design. You can't keep updating it as new things come along. So one of the things that a lot of the general public doesn't appreciate is a lot of the spacecraft, by the time they get to launch, or even the ones that are operating on the surface, whether it's the rovers or other things, they're using technology that is at least 10 years old. And so, we can't make use of the latest and greatest, but it's also important because that older technology tends to have been better tested and qualified for the extreme environments that you're going to encounter in space. So, cell phones have been around a long time, but you can't just launch it into space and expect it to work for 15 years. It isn't. It won't. Yeah. So older chips, older technology, older circuits, have been worked on to do that.
As I said, for me, I'm just thinking about all the modifications and no, this is not up to date. No, we have to use that document. No, we have to do that. I mean, all the smaller details and everything, because the public always see the result and they're not aware of all the work, all the people that is involved in that project, all the headaches people have had to get there, all the huge efforts you're making. It's really awesome, and it's a pity that people don't get to be aware of that, because I think it's incredible.
It is, and I'll just add one more thing, which is there's oftentimes a tremendous pressure to get your spacecraft ready for launch by a specific date, because in a lot of cases, as the planets are moving around the sun as they do, you can't just launch whenever you want. And so, for example, in the case of Dragonfly, if we want to get to Titan in a reasonable amount of time, one of the things we need to do is to swing by Jupiter. Jupiter is, a giant planet, and as you do that, it turns out it allows you to change the trajectory of your spacecraft by its gravity and add a little bit of energy, right? But Jupiter has to be in the right place with respect to where Saturn will be when you get there. And these things are all moving around. So you have to get to launch in time to get to Jupiter at just the right time at the right place, so that it'll swing by and get to Saturn at just the right time and the right place. So not only does everything have to come together and do it, but you're under tremendous schedule pressure. It cannot slip. It's not like a commercial product where you're like, oh, well, we're a little behind. We didn't get the product out this quarter. We'll just delay it by a quarter and we'll ship it next quarter. You can't do that in space. It doesn't work. So there's always that hanging over you, and it's exciting and fun and amazing to be part of these projects, but it's a tremendous amount of pressure too.
Yeah, but I was thinking everything is in a huge scale, huge scale of time, of importance, of pressure, as you said. So it's like everything is gigantic, isn't it?
Yes. Yeah, it is. It's in the big picture, it's gigantic, but then if you zoom in, there are individual detailed tasks at every
Little
level.
dots.
Yeah. So it's
make a huge picture, but yeah.
It's like a Monet.
Yeah.
Right? A painting made up of these little dots, right? And when you back up, there's this beautiful landscape.
That's what I was thinking. Exactly. That's how I was picturing it.
Each one of those dots is a person, and each one is important to make the big picture.
Yeah. And my second question about the models you're preparing about the atmosphere, was it? Yeah.
Yes, yeah. So I use models that are effectively based on the ones that we use for Earth, and they more or less are just like the weather models and climate models that you use to make weather predictions. So the atmosphere is a gas. In physics terms, we often call it that it behaves sort of like a fluid. But in any case, there are equations that describe, mathematical equations that describe the velocity of the air. Air can move in any three directions, up and down, left and right, in and out, right? So there's the velocity, there is temperature, there is pressure. Right? All of those things are related mathematically. And then if you add things like water, vapor, or on Titan, if you add things like methane, there's equations for that, of how that methane behaves and how it can move around. And so we take these equations, which are extremely complicated, and we use computers to solve them. And we do that for a couple of reasons. One is because they're complicated, and although in principle you could take a piece of paper and a pen and write them out, the time it would take to get a reasonable solution would exceed your lifetime by many orders of magnitude. So we need something that's fast right? And so computers allow us to do that. It also computers also allow us to make a little bit of changes and see how solutions change as we change some parameters, which, so again, computers are absolutely essential here, but basically, these models are just a bunch of very, very complex equations that describe the behavior of the atmosphere. And we use the computers to solve those equations, and they tell us how the wind, how the velocity of the air will evolve in time, how the temperature will change with time, how the pressure will change with time. And that is, or, in the case of Earth, whether clouds will form, whether they will rain or snow. And that's what it means to model the atmosphere.
Does it look? I mean, is it like a software you use? You introduce the data and it gives you a result, but how is that result? How does it look like? Is it like graphics?
Yeah. Okay. Yeah. Thanks for asking. The model itself is just thousands and thousands and thousands of lines of computer code, right?
Yeah, that's the backside. Yeah.
Right. And the input is basic things that we know. For example, they're data files. And so as a starting point, for example, one data file might be your best guess or your best knowledge of the state of the atmosphere at a given time. You got to start from somewhere. What's the temperature of the atmosphere at the start? What's the distribution of temperature at the start? What are the winds at the start? What's the pressure at the start? And then that data, which is a data file, the code reads that data and uses that to start solving the equations. And then the output is exactly like that. It's another file full of numbers that describes what the new state of the atmosphere is. How, it started this way. Okay, now it looks like this. At some later time, the winds now look like this. The temperature now look like this. The pressure is this. It's all numbers. Okay.
So you're reading numbers. You're reading a paper with numbers.
Yeah, but and that's so many that a human cannot possibly read it. Right.
Yeah, of course.
Okay. Yeah. I mean, and so we take those files though, and then this is, I think, the part where you say is then we then have additional software that happens after the simulation, after the model run, that analyzes that data and can create maps or graphs that the human mind can interpret, right? So I can say, that's a lot of data, but how does the temperature vary with time at this point? I can go into my data file and, code it up, and a little graph will pop out. Oh, here it is. The temperature goes up and down like this. Okay. And so we have those back-end tools that allow us to analyze the model output. Or we could just make weather maps, which most people see all the time. Right? So the graphics that you see on the news when they're presenting the weather, here's what it's going to look like tomorrow, and they show you the temperature maps. Or we can do exactly the same thing. And all of that data is coming out of the model.
Okay, I have a better idea because, when somebody says model or modeling, I imagine 3D modeling, that it's what I do. So it was like, how is that related to this particular topic? And that helps me to understand your job, which is like really a different thing.
Yeah, we say model, but it's really not. There's a specific kind of model. It's a numerical model. It's a mathematical model, you could say. There are, of course, 3D models. You could actually physically make a model, right? And so, but this is specifically as a numerical model, a computer model.
But you have some graphics in the end because it's what really helps you understand. I mean, in the end, in the back part of that model, there is a lot of code, a lot of mathematics, of course. But what the human eye can read and can interpret, as you were saying, is graphic.
That's exactly right.
It's much easier to read, to understand, and to
that's right.
To compare, also to establish comparisons, to analyze. It's much easier to see and to figure out new things.
That's right. You have it exactly right.
Thanks for your answer. And okay, next super long name. So explain me what it is, the following. The development of the laser absorption spectrometer for volatiles and evolved gas, LASVEGAS, for the Earth's moon and icy moons.
Yeah, wonderful. Okay. So yeah, you got it right. It's the laser absorption spectrometer for volatiles and evolved gas. If you take all those letters and put them together, you get Las Vegas. And so we just call it Las Vegas because it's too much to keep saying it. But so,
next time I will do the same.
Just Las Vegas. And we have different versions of this instrument. It's an instrument that makes measurements, and I'll talk about those in a minute. And you have different versions depending on where you want to measure. If you want to go to Earth's moon, it has one version of that. If you want to go to one of Jupiter's moons, it's similar, but there's some differences and other things. So what does it do? So Las Vegas is an instrument that takes a small sample of the surface of a moon, our moon or Jupiter's moons, or it could be Titan, I suppose. But it takes that in, and it then heats that sample up very slightly just above the melting temperature of water, so just a little bit above 0 degrees C. And what that will do is any water ice or any other what we call volatiles, like carbon dioxide or methane or anything that might have been sort of trapped in that sample of surface, will come out as a gas, just and release. And we catch those gases and we put them inside of a little measurement chamber that's part of the instrument. And our question is, what are those gases? And how much is there of those gases? What's their abundance? And there's lots of ways one can get those measurements, but the way we do it is to shine a laser that goes through that gas. And there's mirrors on either end, so it actually bounces around about 100 times. So overall, you get a very long path through that gas, back and forth, back and forth. Okay, and just like our own fingerprints, gases have fingerprints. Not with actual fingers, of course, but gases will absorb light at very specific wavelengths that are unique to that gas. And so we take a laser and we tune it through different wavelengths, and we look to see when that light is absorbed and when it is not. If it gets absorbed in a specific wavelength in a specific way, we know uniquely that there's a specific gas that must be present. It's a fingerprint of that gas. Only that gas will absorb that wavelength in that way. And so by sweeping through all these different wavelengths, we get a catalog, we get a list of where the light is being absorbed and where it is not. And then we can take that and we can look and identify, there's that gas, there's that gas, there's that gas. Or we don't see a wavelength that, oh, there's none of that gas, right? So either or. And the depth, the amount of light that's absorbed tells us how much of that gas is there. Okay. So it's where is it absorbed? That tells us the gas is there. And how much absorption is there in that wavelength? That tells us how much of that gas. And so it's an instrument to tell us what gases are there and how much of them are around. Okay. That's an important thing you want to do. Let's talk about our moon. There's some practical applications. If you want to send humans there, for example, and have a base, it would be nice to be able to extract water from the lunar surface. But you can only extract that water if you know it's there. It has to be there. So wouldn't it be nice to go around and kind of test, where is water? How much of it is there, right? Here's a spot that has a lot of water. Let's work over here, all right? Or here's a spot that has almost no water. Let's not spend our time over here. Right? There's also, from a scientific standpoint, though, it's also very important to understand how water molecules are distributed on the moon, how methane and other things are distributed. So it tells us about the evolution of the moon. It tells us about its history, where it came from, allows us to test solar evolution processes. So there's lots of scientific reasons to do these things as well. But anyways, that's the Las Vegas instrument. It's about this big. So, about that big, okay? And you can carry it under your arm if you wanted to.
In one of my bags, it certainly fits.
Yeah, if you're an astronaut, you can strap it on your back, right? And it'll tell you what the volatile composition is of the surface.
My God, that sounds complicated. I was wondering, maybe it's a little bit out of the topic, but I was thinking, maybe your topic of research doesn't have this problem I was thinking about. Do you get this question often? I mean, do people ask you why? Let me see how I pose the question, because it's a bit complicated. I was thinking that there is a big or medium-sized part of society that might think that this kind of research is a waste, in the sense that why is people that is not scientific, of course, would think that why is it so important to understand what happens in a planet or in a moon that it's nowhere near us. And these kind of things, because in Egyptology it happens a lot, but I can really understand that in some sense. Maybe in your topic it's less frequent, but do you have that?
We do, and actually it's far more frequent. That type of question or concern, it comes up much more frequently than you might imagine. And so I hope this is okay, I'm going to put in a little bit of a plug for a TEDx talk that I did exactly on this topic many years ago. But you can Google me, right? And TEDx, it'll come up. You can find it. And I believe the title was Space Exploration in an Age of Suffering. Okay, and the basic idea is we have so many problems here on Earth. So many of our fellow humans are miserable and suffering and live terrible lives. And why are we spending money to go study some rock out in space when it could feed, 1 million children, right? And everybody can relate to that question, right? Because we want 1 million children to be fed. We don't want them starving. We don't want suffering. We want to minimize that. So I can appreciate that feeling and that understanding. But I think what's important to understand, though, is that even though maybe not directly, but there's a lot of things that we do in space exploration and in space that alleviate suffering, or that will lead to future developments that will do. So let me give you a couple examples. And I'm not talking about people say, oh, yes, well, NASA invented foam and now we have these wonderfully soft mattresses. I'm not talking about that, okay?
Awesome.
That may be true. That may be true, but I'm talking about bigger things. So, when the space race started, for example, back in the 50s, after World War II, and there was this tremendous space race with the former Soviet Union, the idea there was not even so much for exploration or science or even applications. It was just, we got to get there first. But look what came out of that, which is weather satellites. Now, except for a few people, most of us were born in the age of satellites. We don't know what it was like before we had satellites observing the Earth at all times of day, everywhere. But there are millions of years of human history where that was the case. And you don't have to go back too far into the early 20th century or the late 19th century to see how many tens of millions of people were killed because of a hurricane, or because of a typhoon, or because of flooding, or because of any number of natural disasters. That doesn't happen anymore. Okay? I'm pretty sure it's highly unlikely that we will ever see another day in human history where we will read about how a typhoon or hurricane killed 9 million people. It's not going to happen. Okay, so, spending money to do that turned out to be a good thing. That's not why we did it to start with, but it worked out. Now, the instruments that we use to observe the weather, it doesn't just happen magically. These are highly specialized spectrometers and cameras and other things. And the same instruments that we are now sending out into space, right? All these things, that allows us to do a better job of observing Earth. So the development that we do for sending a highly specialized camera to Mars, like, who cares about Mars? But the technology, the development went into that, then gets turned around and is used to look back on Earth and do a better job. Okay, so there's all of these things that come about. Okay, and I'll throw out one other thing that I make a point in this talk I did, which is that looking forward, everything that we do, this is the law of nature. It's thermodynamics. Any work that you do, any activity that you do produces waste. It's a law, right? You can try to reduce that waste, but you can never make it zero. So when we talk about, for example, green energy and all these are things that we're trying to do to do work, make energy with a minimal amount of waste. But there's always waste, right? And right now, all of that activity is done on Earth. Whatever we do, the garbage, the waste from that activity is on Earth. But suppose you could do a lot of that out in space. Suppose you could go to an asteroid. You could do all that work. You could make things there. You could leave the waste there. There will be waste. There's always garbage. There's always trash. But you leave it there, and you send back the product to Earth. So what you do is now your trash can is no longer on Earth. Your trash can is somewhere out there. We only have one place where we can live right now, and that's Earth. Let's stop messing it up. Let's stop dumping our trash where we live. We can make our lives better. We can have all the products and energy that we might imagine, but we can leave the garbage somewhere else, right? So, and that's only going to happen through investment. It's only going to happen by building better rockets, building better technology. It will happen. There are people looking at how to manufacture things on the moon, how to manufacture things on the asteroids, how to bring resources back, right? So that's the future. Like, imagine a future where there's no industrial waste. Imagine a future where there is no mining waste, right? Imagine a future where we don't have to worry about the emissions of carbon dioxide as we try to create energy, right? Imagine an Earth like that where the amount of waste that we produce is very, very small. That's how much suffering will that reduce? How much better quality of life will that bring to the whole world? And so, I agree. There's a lot of suffering right now, but we have to think in terms of the future too. We want to minimize the future suffering, not just the suffering now. So investment in those kind of things have time and time again turned out to be a great investment. If you want to reduce suffering, if you want to lift the standards of the world, there's hardly a better investment than to do things in space. It turns out to have tremendous positive impact.
Mm-hmm. Okay. Absolutely. I loved your answer because you gave me amongst others, two very important points that I think it's one of them is to be able to recognize the importance of a long-term strategy, because it's sometimes very difficult to see in such a long term, but in the end, we have to. We need to look ahead and see further away, not just what is right in front of us. And also what you said about that once you're there in that long term, you look back and you give the feedback back to the Earth and to society, and new technologies and research. The research is so important to do that, because indeed you do research to achieve something big that is needed for a particular reason at a particular time. but part of what you found out through that research can be used in many other small environments, and that's what we live with, actually, the phones, everything. So I really loved your answer, because I hadn't seen it that way. And I really like it. If you're not too tired of me already, I still have some questions, because we are like talking a lot. Can I continue? Yeah? Okay. Thank you. Okay, the next question was about Titans. Again, about the methane of Titans from lakes to clouds. That's the question.
Okay, yeah, I touched on this a little bit, but I'll go into it a little bit more detail. So as I said, Titan is an amazing place because it has this gas, methane, that behaves a lot like water does on Earth. And so you can make clouds. Those clouds can rain, they can snow, you get runoff, you produce lakes. And it's the only other place in the solar system that does that, right? And what's even more amazing is that, I think, is that it doesn't just make clouds, right? But it makes a whole variety of different clouds, many of which we're familiar with on Earth, types of clouds. My favorite are thunderstorms. Right? So on Earth, those are, thunderstorms themselves. We call them thunderstorms because the lightning produces thunder, the sound. Okay, but these are very deep, violent cloud systems that have very dynamic and strong updrafts and downdrafts and produce lots of rain, even flooding rains. Dangerous things. Titan does this too, but with methane. With one exception, we don't think there's any thunder, because we don't think they actually produce lightning. But they're very deep storms, these storms. In fact, they're 3 or 5 times taller on Titan than they are on Earth. So if you've ever seen a big thunderstorm kind of off in the distance, this thing is even higher. It's 3 or 5 times higher than airplanes fly, okay? Enormous systems that produce insane amounts of precipitation, meters of rain, right, that come down in a very short time and then carve valleys and gorges on the surface of Titan and fill its lake. So the weather there, those cloud systems, to me, are just amazing. And I like to model these things. I use numerical models to produce these storms and understand how they behave and compare and contrast them to how they operate on Earth. And then the flip side is, now you have all these big lakes or seas on Titan, and just like on Earth, they influence the weather. So the lakes or the seas that have methane in them, that methane will evaporate, go back to a gas and back up into the atmosphere, and it'll move around, and eventually it may condense and form a cloud and rain out again somewhere else. So there's that cycle, just like we have on Earth. But as it evaporates from these lakes, and this happens on Earth with water, that lake or sea temperature will cool down, gets a little bit cold due to the evaporation. The air right above it gets a little bit moist, and it forms a marine layer. When you go down to the ocean or the sea or to a lake, it gets a little bit cooler, gets a little more humid, right? And you can even drive circulations that we call sea breezes as that cooler, moist air flows inland, or land breezes. Sometimes the air will flow out over the lake. So it has these weather patterns that are similar to what we experience on Earth. And I like to study those and understand those as well. So I think, the part of this is that Titan is kind of like an Earth, but it's also not. It's very, very cold. It has methane instead of water, but it has a lot of the weather systems and clouds and precipitation systems that we're familiar with on Earth. But at the same time, they're also very different, right? So it's just kind of an interesting compare and contrast, a very interesting place.
Yeah. And what about another project, identifying mesoscale phenomena in the Mars Climate Sounder data?
Yeah. Okay. So these types of projects, these are things I do, start to get a little bit esoteric. So let me just describe what mesoscale is. If you're a fan of your Greek or your Latin, I'm not sure which one it is, but meso means medium, medium scale. So mesoscale is a medium scale, right? So medium scale in the context of Earth means not big, giant weather systems and not micro, little turbulent scales, but kind of everything in between. So what I've been talking about when we talk about storm systems or lake and sea breezes, microclimates, even though it's micro, the scale of the circulation within a Mars crater, those kind of things, those are mesoscale circulations. That's the area, the scale of the atmosphere that I focus on. I'm a mesoscale meteorologist. I look at those middle scale things mostly. Okay, so because that's my interest, I am using data that was acquired from an orbiter at Mars. And that orbiter can look at the radiation, thermal radiation, infrared radiation, coming from Mars and its atmosphere. And that information can be used to derive the temperature profile through the atmosphere. So I've got this data set that has millions and millions and millions of temperature profiles of Mars. And the project that you've described is to sift through those and find interesting things at the mesoscale. All right. And so as you can imagine, millions and millions and millions of these. I can't just look at them with my eyeballs. That's impossible. Right? Click, no, don't do that. So again, we use computer code. We ingest these millions of profiles. We compute statistics on them. We look at averages and deviations. And statistically, what I do is try to pull out things that look a little strange. You know, hey, that's kind of, what's going on there? That's not like all the other ones. Right? So once I start those, now I can start selecting those and try to understand, well, okay, what's causing that little squiggle in temperature that normally shouldn't be there? And oftentimes what we find is that those are associated with mesoscale weather systems. Okay. And so using that data, I can start to identify those things and see what's going on in Mars. And then, of course, because I'm also a modeler, I take my numerical model and try to model that and see if I can reproduce that squiggle that was observed. And if I can do that successfully, it's not definitive, but it gives us more confidence that the hypothesis or explanation that I'm providing to explain that squiggle that we observe might be right. What's causing that squiggle? Oh, I think it's this. Well, let's model it and see. Oh, yeah, it can do that. Does that mean that's what it is? No, but it's a reasonable explanation, right? So it helps try to give understanding to the data that we're observing.
I was thinking, you seem to be involved in many different projects. Are all these projects taking place simultaneously? Are you working on all those? So it's like, you work 8 hours a day and you work in different projects, or do you sleep at all, or do you sleep in the office in front of the computer, or how does that go? Because it seems like a lot.
It's a lot of projects, and so I should and I apologize to my colleagues and friends. I should, and I think I did this a little bit, but I have to acknowledge that I don't do this by myself. I work with others who are doing this. I have students and others who work on some of these things sometimes. I have other coworkers and colleagues that help me with these things. So all of the things I'm mentioning are far too much for one person to do. Okay, so most of these things are a group effort in some way. The ones we've talked about, most of them I lead. I'm directing that, and I certainly do a lot of work there, but I also have lots of really talented and smart and motivated people that are helping me do this. None of us, or very few of us, work 8 hours a day. Partly that's because there's too much work. Partly it's just because we just love doing it, right? And
it helps.
Yeah,
that helps.
Yeah. And and there's also this is not a job, as they say, that you leave at work, right? As you're going through your daily activities, it's not uncommon for me to be doing one thing, whether maybe I'm cooking dinner, but at the same time I'm thinking about some problem. And that's part of my job. It's part of my work of thinking about these things. So it's almost every waking moment I have, most of the time, oftentimes I'm thinking about work or doing work, even if it's just in my head. But most of us also work far more than 8 hours a day, unfortunately.
You suspected that.
Yeah,
slightly.
Yeah.
No, but of course it's a teamwork. It's not an individual job. But anyway, just to pay attention to all those different tasks and topics, and even if they are more or less related, but there are so many specifics. I was looking for the word. That it might be difficult to combine all those projects and keep your brain clear to really do what you have to do in this project and do what you have to do in the other project and not mix them.
It is hard. It does require a lot of multitasking and being able to switch back and forth, and different people have different ways of coping with that. Some people will block out certain days or hours of time to work only on this project and then only on this project. Others kind of, you jump around back and forth, I will say this, I am very, very grateful for whoever invented the electronic calendar. Because with all these projects, it does allow you to keep track of when your group meetings are and when reports are due and when this grant has to be submitted and all of those day-to-day tasks that you have to do to keep all of this research moving forward. There is a lot of administrative work. It's not just doing science. You got to keep track of all this stuff. So calendars are an indispensable tool. So I love my electronic calendar. It definitely helps.
That's good. Okay, I think, I have a couple more questions, but I think it's been long enough for you. I hope it's been at least nice to be here with us. And of course, you're more than welcome to come back to tell us more about maybe something more recent that you're working on or something you want to share with the Spanish public. We would be really happy to have you back. And thanks very much. What time is there? Where are you located, actually?
I'm in Boulder, Colorado, just at the foothills of the mountains, and we are 8 hours behind Central European time. So it's 11:15 here.
Yeah.
And,
here it's night time already, as you can see.
Yes.
Scott, ¿te puedes despedir en español?
Sí. Un poco. Sí. Muchas gracias por la oportunidad. Sí. Es un placer. Y me gustaría, volver en la futura. ¿Sí?
A ver si en la próxima entrevista aprendo inglés para poder hablar contigo también en inglés.
Sí. I apologize. As I communicated, when I have time to think, I can write Spanish reasonably well and fluently. I can read very well. I just cannot talk, and I have great difficulty oftentimes listening because the native Spanish speakers just talk too fast.
But I'm from the south of Spain. You wouldn't understand a single word I say.
No. Well, but I'm learning. But also in the U.S., of course, we learn in school. If you learn Spanish, it's mostly Mexican and Latin American Spanish. So there are big differences in pronunciation, and of course, they do not use vosotros. Right, and so having to make that adjustment to Castellano is a little bit of a challenge also.
In comparison to English, Spanish is a difficult language, the grammar. Well, anyway, we appreciate that you can say a few words in Spanish.
Sure.
We will continue speaking in English. It's not an issue, but I understand the language problem. I work in English and French plus Spanish, so sometimes I also mess up a bit with languages.
Sí, pero estoy practicando mi español y en la futura espero que...
Es que me ha dicho un pajarito que te quieres jubilar en España.
Sí, en el Costa del Sol de Alicante. Espero.
Sí, sí. Muchísimas
We should have
gracias,
lessons in
Scott.
Spanish anyway.
Yeah. Okay.
Thank
Thank you very much.
Thank you very much.
Okay, see you soon.
Well, I hope you found this interview as interesting as I did. I hope to have Scot Rafkin very soon in the future again. He was a lovely person and it was very easy to talk to him, although the topic was pretty difficult, but he made it look a bit easier at least. And please, if you like this content, subscribe to the channel and give us some feedback, comments, and let us know what you like or dislike or what you would like to see in this channel. So, see you on the next episode.